This is lesson 8.7, salt hydrolysis. So a salt, remember, is an ionic compound that's formed with the cation from a base and the anion from an acid. So for example, if we have this base, MOH, with M being some metal, and HA, an acid, with A being some anion, the acid will donate a proton to the OH to make water, and the metal will go with the anion to form Ma. So salt, this Ma, can react with water. And if this reacts with water and releases H plus or OH minus, the pH is going to change. So this is where things get just a little bit more complicated. So the anion, remember, the A minus, is the conjugate base of the acid. And if the acid is weak, the conjugate base must be really strong. So if you have a weak acid and you react it and it's in water, okay, and you form the conjugate base A minus, that A minus is now a strong conjugate base, and it can react with water to form OH minus ions. So this A minus is reacting with water. It's a strong conjugate base, so it's going to grab a proton, and that leaves water as hydroxide. So the pH is going to increase because now you have hydroxide ions in solution. Vice versa, if you have a cation, the M+, remember this is from the base. So when your base is weak, you're going to form a strong acid conjugate. So the M+ is going to be a strong acid. And that too can react with water. So if the M+ is coming from a weak base, that makes it a strong acid. So it's going to react with the water to form MOH and H+. So in this case, your pH will decrease. And when the cation is a metal ion, your outcome depends on charge density. So if your cation is +3 or +2 charges, very small things, you're going to hydrolyze water, so your pH will go down. But group 1 and group 2 cations do not hydrolyze water. So anything in group 1 or group 2 will not hydrolyze water. So here's just a summary of what can happen in each of the following scenarios. So if you have a strong acid plus a strong base, for example HCl plus NaOH, the salt you're going to form is NaCl. So neither of these, the cation or the anion, is going to be strong because remember these are both strong, so they're going to be weak conjugate base, weak conjugate acid. So nothing's going to happen to the water and your pH will stay 7. But if you have a weak acid plus a strong base, for example acetic acid and sodium hydroxide, you're going to react to form water and sodium acetate. Now, when you have sodium acetate, you had a weak acid, so this is now a strong base. So because this is a strong base, you're going to hydrolyze water and your pH is going to increase. So your pH is actually going to be just a little bit bigger than 7. If you have a strong acid and a weak base, for example HCl and NH3 or HCl and aluminum hydroxide, you're going to form products where you now had a weak base, so your conjugate acid will be strong, and so your pH is going to be less than 7 because it's going to react with water to form an acidic solution. And then last but not least, if you have a weak acid and a weak base, for example acetic acid plus ammonia, you're going to react to form ammonium acetate, and these depend on the relative strength, so whichever one is stronger is going to dominate. If ammonium is the stronger conjugate acid, or if acetic acid is a much stronger conjugate base, that is what is going to determine the pH of your solution. So the last type of titrations that we're going to talk about involve weak acids and bases. So here's an example. If we titrate a weak acid like acetic acid with a strong base like sodium hydroxide, our sodium hydroxide is going to dominate the pH at the equivalence point. So if you have a weak acid plus a strong base, your pH is going to be greater than 7 at the equivalence point. And this region here in the beginning, where the pH kind of stays relatively the same as you have weak acid, weak acid, weak acid, and you're slowly adding strong base, this is called the buffer region, okay? Because you're starting with a weak acid, remember, to make a buffer, you start with a weak acid and you add strong base until half of it has reacted. So this buffer region right here is where the pH stays the same. And exactly halfway to that equivalence point, remember here's the equivalence point, halfway to that point, this is when half of that acid has been neutralized. So this is when you have the perfect buffer and you have a mixture of equal quantities of weak acids and its salt. So right here at this halfway point, this is where you have the perfect buffer, and to find the pH here, you can use the Henderson-Hasselbalch equation. So the pH right there, halfway to the equivalence point, is going to be the Henderson-Hasselbalch, so pKa plus the log of the salt over the acid. Now, if we have the opposite, a strong acid and a weak base, for example, HCl and NH3, so here we're starting with NH3 and we're slowly adding HCl. Again, we get this buffer region set up, so right here, halfway to the equivalence point, we can use Henderson-Hasselbalch to find the pH. And as you can see, now we have a strong acid, so our equivalence point, the pH is going to be less than 7 because the strong acid is going to determine the pH there. Okay, the last type of acid-base reaction is a weak acid and a weak base. And the pH at the equivalence point for this type of titration is hard to find because your titration curve is much more gradual. So we don't usually titrate a weak acid and a weak base.